And then we will go a little bit further away, discovering strong gravitational lenses in unions with CFIS. This is presented by Christopher Storfer, University of Hawaii, Institute for Astronomy.
Hello, everybody. Very happy to be here. Today I'll be talking about my work in discovering strong gravitational lenses in unions, of course, including CFIS data. And so I wanted to start off the presentation by showing a known lensing system that we discovered somehow in the previous Northern Skies survey, which included observations from the Bok telescope. I don't know how we found this system, given data quality here, but we ended up getting HST observations for this system. I wanted to show these two images just as a comparison for the CFIS image quality, which is quite exceptional. And it's really played an instrumental role in the success of this project. And you'll see that as we go through the presentation. First, there's an image that isn't showing. I had an image of me in front of the Keck telescope, but it's not there for some reason. But in kind of along the lines of what we've been talking about throughout this conference, earlier today and yesterday, I wanted to introduce myself, where I'm from, and how that's played a role in my life. I've just added this slide today, so if I go over time, this is why, and I think that's okay because this is important. I was born and raised in Hawaii, and I went to undergraduate at the University of San Francisco, where I worked at Lawrence Berkeley Lab with a bunch of the DESI folks who helped me start my career. And eventually I returned back to Hawaii, where I'm now a graduate student at the Institute for Astronomy, being advised by Eugene Meunier and David Schlegel, who's here. And the theme of the conference really resonated with me as somebody who was born and raised in Hawaii and found themselves going back. And I want to, express my gratitude to Hawaii, the people of Hawaii, the indigenous people of Hawaii. They're the reason why I'm here, the reason why all of us are here. And so I really wanted to include this. So thank you. Thank you for having me as well. But the talk today will be focused on my recent paper, just finding gravitational lenses in unions. I'd be happy to discuss this with anybody. You can reach out to me via my email if you don't find me before the conference ends. For those who are less familiar with strong lensing, it's a rare phenomenon that occurs with the chance alignment of a massive foreground galaxy or lens and a background galaxy or source. And that as a light from the source travels through the gravitational potential of the lens, it gets deflected. And this produces multiple highly magnified and distorted images of this background galaxy. You can see that manifests here as 4 images distorted into this arc or ring-like structure. And the nature of strong lensing really enables it to be a very powerful, multifaceted tool in astronomy and cosmology. In particular, it's capable of providing independent measurements of the Hubble constant. But something that I'm interested in is its ability to act as a probe of dark matter at cosmological distances. And this is to just set the stage for why finding these systems is very important. A little bit more context, right? We exist in the cool dark matter paradigm, which dictates this hierarchical structure formation. And strong lensing has historically been a very powerful probe of CDM at a wide variety of scales, from the largest clusters to groups of galaxies, single galaxies, and even at subgalactic scales. And I'm interested in particular in the single galaxy systems. This is because we can very accurately probe the distribution of their mass profiles and understand quite a bit about their evolution through cosmic time. And so with that, this is the broad context of my dissertation goals. We want to find strong lenses, we want to follow them up spectroscopically to obtain redshifts, and we want to model them so that we can extract physical parameters from these systems. Today, of course, I'll just be talking about finding these systems. I mentioned they're rare. It's estimated about only 1 in every 10,000 galaxies acts as a strong lens. However, we found quite a few of them over the past few years. So I think we're sitting at around, this is slightly outdated, we're sitting around about 10,000 candidates in total. And you can see the discovery rate really accelerated around 2018. At this point, the use of convolutional neural networks in the search for strong lenses really increased. And the reason why convolutional neural networks were necessary is because we were encountering larger and larger data volumes with these wide field ground-based imaging surveys. And so these surveys are all fantastic. and they've been really helpful in discovering rare objects like strong lenses. And I'm just showing a few examples here, but all these surveys have, their own unique combination of depth, area, and image quality. And as you can imagine, the specific combination of these qualities dictates how useful they are to find strong lenses. For instance, Pan-STARRS has incredible area, but suffers slightly in the image quality, whereas HSC has incredible depth and image quality, but suffers a bit in terms of the area. So you can imagine where I'm going with this. UNIONS, which you've heard a lot about this week, has quite a unique combination of survey area, image quality, and depth. And I think that it makes it one of the best, if not the best, for finding large volumes of strong lenses relatively efficiently. And so with that, this is the data set that we are working with. People have told you throughout this week that UNIONS is complete above Deck 30. We started this project way before it was done. So this is the data that we started working with when the project started. And we choose the GR and I band in particular because it holds very valuable color information for the systems that we're interested in. And you can see that system that I showed in the first slide here in the GR and I. Of course, the G band contains very useful information about our source galaxies, which typically are emission line galaxies. Jumping to the right to the I band, the I band contains useful information for the lens, which are typically elliptical galaxies, and the R band is a nice blend of the two where we get lens and source features simultaneously. And I'll go back to this a data footprint that we're using. This is about 4,100 square degrees. Again, as you can imagine, we'll be using a convolutional neural network to search this area for strong lenses. A brief refresher on convolutional neural networks. Essentially how they work is running a convolutional kernel over image data in a series of layers. And this is in order to extract high-level feature information from the image data. And so at the end, I don't know if I have the cursor, I don't. At the last convolutional layer, we end up with a set of feature maps, what we call feature maps, and we can flatten these and then eventually condense them down to a single number. And in this context, this number represents the probability of an image containing a strong lens. So 1 being a lens, 0 being not a lens. Well, for those that are particularly astute in machine learning, we use a residual convolutional neural network, which allows us to build out a deeper network, but I don't have time to explain all the details there. So typically these networks are trained on on simulated images of lenses. However, we take the approach of training it on real data of known lenses that are identified within the UNIONS footprint prior to our work. We also include a number of what we call non-lenses, and this just includes everything that is not a lens. The spiral galaxy, image artifacts, just regular galaxies, basically to tell the network what a lens is not, right? Which is equally as important as telling it what a lens is. And in this training process, taking advantage of certain data augmentation techniques, data pre-processing techniques, especially in a survey like UNIONS where you have data from 3 different telescopes, it's really important to create as homogeneous of a sample as possible. And so we do a lot of work augmenting our data before the network even sees it. And after the network sees the data, we can spend a lot of time optimizing hyperparameters, how we train the network, how fast it learns, and this really affects our performance. And I don't have time to explain exactly what this plot means, but I'm just showing the performance of the model throughout the training process. The goal is to get those solid lines up to 1. We don't quite get there, but what I'll say is that these models are good enough, and we have 2 of them. So we'll take advantage of these 2 decently well-trained models in combination to search the UNIONS footprint for new lenses. But first, we need to define our deployment sample. And because there is no grand unifying UNIONS catalog yet, unfortunately, we make use of the tractor catalog from the DESI Legacy Service, thank you, Dustin. And there are about 8 million objects which overlap with UNIONS and are above our magnitude cut. So we deploy 8 million objects, and we take the images which receive a probability. Basically, I should say, we combine the probability outputs of the network with an OR gate. So we set a threshold, and if either of the networks are above that threshold, we take it. And we call these neural network recommendations. These recommendations are then subject to human inspection, and from that we find 1,346 new strong gravitational lenses. We additionally grade them by quality, grade A, B, and C, representing definite, probable, and possible strong lensing candidates. And you can see them on the map of the combined GR&I area there. And I'm very pleased to say that this paper is the second largest single sample of lenses reported in ground-based imaging surveys. I put a couple of asterisks there that we mostly explained in a couple of slides. But this is probably what you've all been waiting for. These are lenses that we find, which mostly show up okay on the projector. These are a random sample of our grade A systems. So these are the definite systems. And then grade B and grade C, the probable and possible. And I really want to emphasize, this relates back to the asterisks on the previous slide. We maintain an extremely high quality and a high standard for our grade C candidates, much higher than I've seen in some other works which report strong lenses. And so I want to take a look at this very convenient figure from actually one of the Euclid strong lensing searches. You can see here, this union data point was put there before our search. This is a combination of a couple of previous searches from earlier years. However, after our search, we can see, I should explain what this plot shows. It shows the area of the survey on the x-axis and the number of lenses per square degree on the y-axis. And you can see, while we search a slightly smaller area than past union searches, we discover lenses at a much, much higher rate, about 1 per every 3 square degrees. And I believe that we can do a lot better, which I kind of alluded to when I showed the training performance of the neural network. This is where I think we can get to and end up with a sample of about 3,000 or 4,000 lenses discovered in unions. And so we can take a look at the characteristics of this lens sample. And while I'm running out of time, I'll just breeze through this relatively quickly. The neural network does an excellent job of discovering lenses out of sample. And so in this particular case, we can look at the redshift distribution for our new candidates and compare that to the redshift distribution for the lenses that were included in the training sample. And of course, the training sample is representative of the known lenses. So you can see that especially in the redshift 0.6 to 0.8 bin, we do quite well in terms of the rate of lens discovery compared with the training sample. And this is particularly valuable because this is the range in redshift that I'm particularly interested in, especially when probing the evolution of elliptical galaxies. So quite convenient for me. I've talked a little bit about improvements, so I'll breeze through this again. I'll mention that we had some overlap with discoveries in the Euclid Q1 lens searches. 10 systems that we found overlapped with EDFN. Euclid found all of them. And so, what does this mean for the future of strong lens searches and unions in the era of Euclid? I think, one, we can capitalize on the time that we had before Euclid observed the entire union's footprint and still find lenses. But I think the next step is to make simultaneous use of both ground-based and space-based data, combining the useful color information that we can get from unions with the extraordinary image quality that we can get from Euclid. And I'll end with this slide as a summary and take any questions if we have time. Thank you.
Thank you. We have time for one quick question.
Thank you for this very nice talk. I was looking at the distribution of lenses on the sky, and it looks like it's not homogeneous. Is there a correlation with seeing, or what does it correlate with?
Yeah, I've looked a little bit into this, and it's not entirely clear. I think that it's mostly correlation with depth, actually. But I think there is also some effect from seeing, and in my paper, you want to go check it out, as a plug, it has maps of the depth, and you can see that there's some correlation between the depth and the density of candidates, but we don't fully address that in the paper. I think this could also be indicative of a shortcoming of the training sample. We use known lenses, right, which is great because it's in-sample data. However, they may be biased, like from where they appear in the survey or how they appear in the survey, based off of various factors, right? So understanding neural network bias is a very difficult thing, something that we should do, but not something that anybody's done quite yet in this context.
Thank you. Let's thank our speaker again.